Okay, get back to the first screen here. Okay, so in this section, we're going to be looking at discontinuities. And so functions can have two types of discontinuities. The first, and this is a discontinuity is a place where the function is not continuous. So if you're thinking about tracing the function with your pencil, you're going to have to pick up your pencil to trace it. The first type of discontinuity we're going to talk about are removable discontinuities. And removable discontinuities are going to look something like this. You'll have your graph, and you'll have some sort of function that's on that graph. It could look like anything. It could be a line. It could be something like this. And somewhere on that graph, you have a hole in the graph. So it's just one single little point where the function is not defined for that value. So these are called removable discontinuities because you could remove them by putting one tiny little point right there, and then the function would be continuous. These are also often called holes in the graph. You'll hear me call those holes very often, but their fancy name is a removable discontinuity. You also have a couple types of non-removable discontinuities. So there are two that we're going to look at, and one in particular we're really going to focus on finding today. So the first type of removable discontinuity that we're going to look at is called a vertical asymptote. And you guys should have seen vertical asymptotes in other classes. You may not have found them algebraically, but it's a vertical line, and as your function approaches that vertical line, it's going to get closer and closer and closer to that line, but it's never going to actually touch it. You could have it approach from just one side like we see here, or it might be one where it approaches that line from both sides of the graph. But either way, you would have a discontinuity here, because to trace this, you'd have to pick up your pencil and jump down here as you continue. I guess these should have arrows on this side as well. So vertical asymptotes, this is an example. I guess I should write it right here. Vertical asymptote. Vertical asymptotes are one type of non-removable discontinuity. The other type of non-removable discontinuity that we're not going to focus on a lot today, but I want you to just know that it is there, are jumps in the graph. When we were doing piecewise functions, we might have an absolute value function. It might end right here with a closed circle, and then you might have a jump down here to a quadratic. It looked like that. So these are jumps in the graphs, and most of the times those jumps in the graph come from piecewise functions that are not continuous. So that piecewise functions we looked at very early on in the class, we are not going to go back over those in detail right now. We're mostly going to focus on vertical asymptotes. So let's continue. There are several features in an equation that can cause discontinuities. The big one that we're going to look at today is zeros in the denominator of a fraction. If you have 0 in the denominator of a fraction, that makes the function undefined. You also cannot have negatives under a square root. You cannot take the log or natural log of 0 or a negative number, and you cannot have piecewise functions that are not continuous, because those all cause discontinuities. However, the big one that we are going to focus on here is this first one. These others also cause the domain to be restricted or for there to be discontinuities, but the first one's the one we're really going to focus on in this section. So here we are going to graph this equation, f of x equals 2x minus 3 over 2x minus 3 times x minus 4. And we're going to describe any discontinuities. So I believe I have that saved. Let me insert this graph here. I graphed this one in Desmos just a little bit ago. Oh, that's the giant graph. And we make that smaller there, we can see the graph here. Okay, so if I look at this graph right here, I can tell that right here at x equals 4, I have a discontinuity. I have a vertical asymptote there. That's very obvious from the graph. And if you look up here at the equation, clearly if you plugged in 4 right here, you'd have 2 times 4 minus 3 over 2 times 4 minus 3 times 4 minus 4. And so up here in the top, that'd be 8 minus 3, which would give you 5. But down here in the bottom, you'd have 5 times 0. So you'd get 5 over 0, which is undefined because you got that 0 right there in the denominator. So you have a vertical asymptote at x equals 4. However, this graph also has another discontinuity that you can't really see. Because if we look at this denominator right here, we can see that this part right here would be 0 if x equals 4. Well, this part right here, it can also not equal 0. So if I take 2x minus 3 and I set that equal to 0, I could add 3 to both sides, and 2x equals 3. And then I could divide both sides by 2. And so x cannot equal, I'm sorry, I shouldn't put the not equal there yet. X equals 1.5. So right here at 1.5, it does not really show up on the graph, because if you graph these on the calculator or on Desmos, you're not going to be able to tell that there's a hole in the graph right there. But there is a hole in the graph, because if we plug in 1.5, if we do 2 times 1.5 minus 3, hold on, there's strike. Sorry about that. So if you plug that in, you'll have 2 times 1.5 minus 3 over, or times 1.5 minus 4. And so here you end up with 2 times 1.5 is 3. So you get 0 in the top, you get 0 in the bottom. 0 times 2.5, you end up with 0 over 0, which is actually the indeterminate form, which we will learn about in a little bit, but you don't know now. But this is undefined with that 0 in the bottom. So you have a hole in the graph right here. So the question is, how do we tell when there is a hole in the graph and when there's a vertical asymptote? Okay, and so if you look up here at the equation, you'll notice that right here we had a 2x minus 3 in the numerator and a 2x minus 3 in the denominator as well. So those two right there really technically will cancel out. And so if they cancel out, then they don't cause a vertical asymptote. All they cause is a hole in the equation, or in the graph there. This part over here, this x minus 4 that did not cancel out, that causes a vertical asymptote. So whenever you're looking at these rational equations, holes are removable discontinuities, will result when you have zeros in the denominator that will cancel. But vertical asymptotes, which are non-removable discontinuities, that will result when you have zeros in the denominator that, oh, I think I read that wrong. Let's see. When zeros in the denominator that will cancel, here, zeros in the denominator that do not cancel for vertical asymptotes. So, you are going to have an assignment in Delta Math, and in Delta Math, you're going to have basically 3 things that it's going to ask you. The first thing is just going to ask you for which values of x is the expression undefined. And so for these, it doesn't matter if it's a whole or a vertical asymptote. What you're looking for is the denominator to equal 0. So, for example, for this problem right here, the denominator and the denominator only, 7x plus 3, cannot equal 0, because if it does equal 0, then you get a 0 in the denominator. So if you just solve that real quickly, you would subtract 3 from both sides. You have 7x cannot equal negative 3, and then you divide by 7. Okay, so x cannot equal negative 3 over 7. So you would type in negative 3 over 7. Don't put the x equals or x is not equal. Just type in negative 3 over 7. And that is the value where this discontinuity is, where the expression is undefined. So that's the first thing that Delta Math is going to ask you to do. Another question that you might see, or that I would like to work you up to, Delta Math to actually ask you for them separately just because the limitations of typing things in, is to describe any discontinuities. So for example, right here I've got f of x equals x squared minus 4x plus 4 over x minus 2. So I know for a fact the discontinuities only come from the denominator. So I know I have a discontinuity at x equals 2. Because if I say x minus 2 equals 0 and move that 2 over, I'll get x equals 2. So I definitely have a discontinuity at 2 because that gives me a 0 in the denominator. Now, the question is that discontinuity a hole in the graph or is a vertical asymptote? And in order to tell if it's a hole or a vertical asymptote, I'm going to have to factor what I have here. So f of x is going to equal, if I factor the numerator here, it's going to factor into x minus 2 and x minus 2. In the denominator, I just have a single x minus 2. So one of those x minus 2's will cancel. Since those cancel right there, that tells me that this is a non-removable, I'm sorry, a removable discontinuity, or I can also call it a hole in the graph. So that's a removable discontinuity there. So the numerator is really, when you're thinking about these questions, it's only there to tell you whether or not you have a hole or vertical asymptote. The denominator is what's going to tell you if you have a discontinuity at all. So for example, if you had one without a denominator at all, it would not have a discontinuity. It'd just be continuous everywhere. Okay, here's one like you'll see from Delta Math. It says find all vertical asymptotes in the following function, 3x squared plus 20x minus 63 over 9x minus 21. So we know here that you're going to have a discontinuity because you got that 9x minus 21 in the denominator. What we want to know, is it a vertical asymptote or not? So the first thing that I would do here is I would factor, and I'd factor the numerator and the denominator. And it looks here in the top, well, we're going to have a 3x and an x. And let's see, this one's not the easiest. 63 is 9 times 7. Would that be a minus 9 plus 7? Possibly. That would give us a 7x and a negative 27x. Those signs would be wrong, so let me switch those signs. Let's make this one a negative and this one a positive. So it'd be negative 7x, positive 27x. That would work. So you've got 3x minus 7 and x plus 9. In the denominator, you've got 9x and 21. You could divide both of those by 3. So you have a greatest common factor there. So if you factor out a 3, then you would have 3x minus 7. And sometimes that'll sort of help you figure out how to factor things, because you'll see here that 3x minus 7 cancels. So for this particular problem, since that cancels, this part right here gives you a hole in the graph, not a vertical asymptote. So this has nothing else left in the denominator except for that 3, which is not going to equal 0. So this one would have no vertical asymptotes. So you would choose no vertical asymptotes there and submit your answer. Okay, here's another one, again asking about vertical asymptotes. You would need to factor. And so if you factor in the numerator, that would be x plus 9 and x minus 9. In the denominator, you could factor out a 3, so you'd have 3 times x plus 9, and the x plus 9's will cancel here. So since those both cancel, that's a hole in the graph there, x equals negative 9, so you do not have any vertical asymptotes for this either. Remember, you're only looking at the denominator for your discontinuities. This x minus 9 up here in the top doesn't do anything as far as the discontinuities go. So you'll just say no vertical asymptotes for that one. And then, of course, if you have something where you do have, for example, if this did not cancel and you had an x plus 9 left in the denominator, then that would mean that you would have a vertical asymptote at x equals negative 9. Okay. The other thing you're going to get from those questions is it's going to say to find all holes of the following function. Write your answer as a coordinate point in the simplest form. If no hole exists, press the negative icon right over, that's right over here, to indicate there's no solution. So, for these, again, the first thing you want to do is factor. So the numerator here will factor into x plus 4 times x minus 4. The denominator, I would factor out a 2 first, which will give you x squared minus 2x minus 8. And so if you factor that further, you've got x plus 4 times x minus 4 over 2 times, we're going to factor this part, we have x and x, and we're going to do minus 4 plus 2 will give us that. So you've got an x minus 4 that cancels. So the hole on the graph is going to be at x equals 4. So you'll put that in and submit your answer. The hole is the one that cancels. Now this one would have a vertical asymptote at x equals negative 2. On your Delta Math assignment, it is not going to ask you for both of those at the same time. I'm sure that's probably just because that's more difficult for them to program in, and they did not do the questions that way. But this one would also have vertical asymptote there. So now you're going to go do that Delta Math assignment. If you have any questions, let me know, and I'll try to help you with those.